Now we are going to look at the model. So the model that we have is taken from TN 2011. In this model, we have three populations of cells. We have the healthy tumor cells, the infected tumor cells by Y, and we have the free virus. So here, the healthy tumor cells are being infected with the rate A, and they are eradicated with the rate delta. So we have the burst size of the virus B, and its clearance rate is C. So here the most important parameters are A, B, and C. And after calculating the reproduction number, we have it's equal to A times B over C. A quick analysis of stability analysis, we have that the extinction equilibrium is unstable. We have the stability of the virus-free equilibrium when R0 is less than 1. And we have the coexistent equilibrium. So we can do a bifurcation analysis. And bifurcation happens when B is equal to C over A. And so using the base parameter values, we have that B0 is equal to 24. And simulations, okay, these simulations are going to verify with what we just saw. So we saw that the bifurcation value was 24. So when we have B equal to 10, we have the stability of E1. And at 24, the oscillations start. And so this can help us to, so looking at this value, a very large burst size, we can see that we have almost the eradication, complete eradication of the tumor cells at this value. This gives us a hint that for the tumor to be eradicated almost perfectly, we need a big burst size value. Okay, but we talked about immune system, but we didn't see it in our model. So now we're going to incorporate immune system inside the model that we had. So we separate the leukocytes into two parts. We have the tumor-specific ones shown by LX, and we have the virus-specific ones by LD. So the healthy tumor cells are being eradicated or killed by the tumor-specific one. When the tumor cell is infected, we have both LV and LX here, and the virus is only being killed, of course, by the virus-specific leukocyte. Okay, we are going to use this model now. This is going to be our base model, and we're going to combine different therapies with this model that we have here. And this is just the simulation of the model we just saw. Okay, so we're going to combine it with 7 different therapies here. So we're going to go through the model one by one, and at the end, we're going to have a comparison of all of these. So we start with continuous infusion chemotherapy. In this therapy, we have the patient is receiving the chemo drug continuously over the treatment period. And this drug has both effect on the tumor cells and the leukocytes, and it has the concentration of C. We have the response function here, E, and mu is the toxicity coefficient for each X, Y, and for L is the same. Okay, next we have brachytherapy here. The radioactive seeds are planted very close to the tumor cell. And so R is the dose of radiation at each time T. And again, they're going to have an effect both on the tumor cells and the leukocytes. Next, immunosuppression. As we said, the immune system was like a problem. To remove that, we try to remove the leukocytes by the drug I with concentration. Okay, with the drug with concentration of I, and yeah, they have the model here. Next, we have active immunotherapy. Here, a sort of drug is injected to the patient. So its job is to help it modify the activation and the activation of the tumor-specific lymphocytes, it is different with just enhancing the immune system because it's only affecting the tumor-specific lymphocytes. So here, when zeta and kappa is greater than 1, we have that there is clearance and activation rates are being enhanced and modified. So next, we have passive immunotherapy. In this one, the difference is that the lymphocytes are removed from the patient and they are in the vitro. They are activated so that they can, oh, sorry.
I'm sorry, on the previous slide.
Yes.
On the active immunotherapy, is there a reason why activating the immune system is only increasing the efficacy against the unaffected tumor cells, but not the affected tumor cells? If I'm reading that right, because you only have the cap on the X, but not on the Y, right?
Yes. I think there should be kappa here. Isn't it? Yeah, there is one. Yes. There should be one here. Yes.
Yay, okay.
Yes. Sorry, yes.
Sorry.
Yes, thank you. Any questions? Okay. We have passive immunotherapy. So the lymphocytes are removed from the patient. In vitro, they are modified and so that they can identify the antigens by the tumor, and they are injected back into the patient and they have like antibody to kill the tumor cells better. Okay, and we have the infusion rate of fee for this therapy added to the tumor-specific leukocytes. And fractional chemotherapy. Here it's, so the dose of the chemo drug is being administered to the patient in equal doses during the time of period instead of being as continuous. So here they have almost the same model. Here we don't have one. So when the drug is being administered, this is equal to 1. For the rest of the time, it is equal to 0. And the last one, we have the external beam radiotherapy, which the tumor cells are being killed by the radiation from outside of the body. And after each treatment, all but a surviving fraction of the tumor cells and leukocytes are going to survive. And we have the surviving fraction S equal to this equation we have here. D is the dose, and alpha and beta are the radiosensitivity of the cells to 1 or 2 doses of radiation. Okay, now we have all these models. Now we need a tool to compare these. So we're going to use tumor control probability. And so here we have, so it's usually used for radiotherapy, but here we're going to define the surviving fraction for the other types of treatment to be, at each time to be the number of healthy and infected tumor cells. So as we saw before, when beta burst size was big, the virotherapy was kind of successful on its own. And now we're gonna see the simulations for this value of 3,500. Yes.
Tau is just non-random time.
Yes. Yes.
So it's not stored.
Yeah, what do you mean by Poisson? I'm confused.
Sorry?
What do you mean by Poisson? It's not a stochastic model, it's a deterministic model, right? I'm missing something.
So at each time of t, at any time, we have the surviving fraction is the number of the tumor cells that are left.
Right, but there's no stochasticity.
No. Oh, maybe yeah.
But what about M naught? Is it a random variable or is it like non-random?
It's the initial number of the cells.
Right, non-random initial number of cells.
Yeah, the word Poisson is confusing.
Yeah,
This
because-
Poisson is.
No, but there are different models for the tumor control probability, which is the extinction probability of a stochastic process. And if you assume that the burst death process is a Poissonian process,
What process is
the burst death process, underlying the survival of the tumor
I
cells.
understand.
Yeah.
What do you assume to be for solid?
But you assume,
So number
I
of.
think it's just a constant rates. Constant rates.
But there's no stochasticity in this paper, is that correct? Everything's deterministic, is that correct?
We just use the Poissonian TCP because there are other TCP, there's a Vernonian TCP, there's a Zeiger-Minerva TCP, that use different stochastic processes. To do us. Okay.
Because
Yeah,
of course,
yeah,
when you
that's-
like to get,
yeah.
you seem to be able to come some numbers.
Yeah.
Consume.
Yes, go ahead. Yeah, we'll talk later.
Okay, thank you. So now, first we're gonna look at the simulations. So here, for the other ones, we're gonna have the biotherapy alone here, and the therapy here, and we're gonna have the combination of these two down here. So the red is the TCP, and the blue is going to be the tumor load, both types. So now what we hope to see is a higher TCP in a shorter number of days. So here, for instance, we have after 20 days, we have TCPs around a half. For this therapy, continuous infusion chemotherapy, after almost 50 days, we have TCP around 1. But after combining these two, we're gonna see that TCP goes around almost 1 after almost 12 days. So this is showing the improvement of combining these two together, and we're gonna get a better result. So we're gonna have almost the same pattern, see the same pattern for the other ones. So here we have brachytherapy. So it almost takes 100 days for the TCP to get to almost a half. By combining these two, we're gonna see that after 15 days, we have TCP is around 1. So we have immunosuppression here. So here, of course, the tumor load is gonna increase very fast because we are taking the only defense the body has, which is this immune response. But combining these two, so it might not reach to 1, but we're gonna see much higher after 20 days. And active immunotherapy, again, we have a higher TCP, shorter, in the same number of days. We have the passive one, passive immunotherapy, fractional chemotherapy, and external beam radiation therapy. So this might not be obvious which one is working the best. So what we did, we needed to compare these two. So I think the best therapy would be one that has highest TCP in the shorter number of days. So we came up with this treatment success measure, which is the TCP squared over the log of Tmax. So Tmax is the predicted number of days for TCP to reach its maximum in 100 days. So calculating this number, we have these values here. So the best one is the highest one. So we have almost very similar numbers, but we can see that we're getting the best result for fractionated chemotherapy and continuous infusion chemotherapy. But this was when we combined the therapy with a partial successful biotherapy. What happens if OBT itself is not successful? Is it going to improve it? Is it going to make any difference, or is it going to stay the same? So we here in the simulations, we're not going to consider the immune response because OBT was failing on itself, and OBT was going to make things even worse. So what we did, we disregarded the immune response. So because of that, we have to disregard these two therapies as well. Okay, now very quickly, we're just going to look at the graph. So OBT is failing. As we said, B is very small. And now we have this therapy here. And unlike what we saw before, we almost see no difference here. So after 50 days, okay, it's not just making things worse. It's just going to stay the same. We're going to see the same for the other ones as well. So this is brachytherapy. This is passive immunotherapy. These are almost the same. Fractional chemotherapy and external beam radiation. So what can we conclude here? After combining these two, we can see that when biotherapy is partially successful, benefit can be gained from this combination. But if you have a weak virus, combining these give us almost no benefit. So we saw that one of the ways to improve OVT was to increase the burst size, but there are other parameters involved too. We can also increase the viral spread rate or decrease the viral clearance rate C. Okay, that was it. Thank you.